What is going on, guys? Welcome back. In today's video, we're going to learn how to do deep reinforcement learning with OpenAI Gym and Tensorflow. So let us get right into it. Now, before we get into the actual tutorial, I would like to mention that this video was sponsored by IP Royal, and I encourage you to not skip this part because this could be very interesting to a lot of you guys since this is directly related to data science and machine learning. Oftentimes when we do data science and machine learning, we don't work with just a CSV file that we load from our file system. We have to gather the information, the data ourselves using web scraping and web crawling, for example. And one problem with that is that if you do it from one computer or maybe from 5 computers, you have a very limited amount of IP addresses that you can use. And the problem with that is that providers, APIs, websites are just going to block you over time because you're sending too many requests too frequently. The solution for that is to use a proxy server and to use multiple different IP addresses to rotate proxy, so to say. And the problem with this is that, of course, you can try and use some free proxy lists, but there are multiple issues with that. First of all, you cannot trust those people that provide these servers. Why would anyone provide the service for free? Can you really trust them? I think not. Second of all, they're unreliable. A lot of these free proxy servers don't work at all. They work maybe for a day or two, and then they're basically useless. If you need something reliable and serious, you can use IP Royal. They provide 100% transparent proxy services with a lot of IPs that you can use. And basically, you can connect from different locations. You can do large-scale professional web scraping using their services. You can go to their website, iproyal.com. You can look at their services. You can look at their pricing. And the good thing about this promotion here, about the sponsorship, is that you can get 30% off with the coupon code Neural9. So make sure you check out iproyal.com in the link in the description down below. Alright, so we're going to get started by installing a couple of external Python packages first. And for this, we're going to open up the command line and we're going to type pip install followed by the package names that we want to install. And the first package that we want to install is the OpenAI Gym package, which is going to provide the environment for reinforcement learning. So it's going to provide the ecosystem that our agent will be operating in. And in order to install it, we just say pip install gym. And for compatibility reasons, we're going to specify an exact version. We're going to say gym equals 0.25.2. The reason for that is because we need this to be compatible with the version of Keras RL2 that we're going to use, because we're now going to also install TensorFlow and Keras-RL2, so Keras Reinforcement Learning 2. And this module here is compatible with this version of OpenAI Gym. This is why we need to install it that way. And if you don't have it installed already, you want to install NumPy as well. In my case, all of these are already installed, so I don't have to do anything. Once you have everything installed, you can start by importing Gym, so OpenAI Gym. And we're also going to import here from core Python the random module, because what I want to do first here is I want to show you the environment that we're going to use. We're going to use the card pull environment, which is just the task of balancing a stick or a pole. So by moving left and right, the stick should not fall, or the pole should not fall. And we're going to try to use a random agent. So the random agent basically chooses randomly if he goes left or right. And then we're going to use an intelligent deep learning reinforcement or deep reinforcement learning agent to see if it performs better. So we're going to create an environment by saying gym.make. We're going to make a card pull-v1 environment. This is an identifier. You also have different environments that you can use, but this is a very simple one because we can only go left or right. So we're going to make that environment, and we're going to set the render underscore mode to human so that we can actually see what is happening here. And then what we want to do is we want to go through a couple of episodes of just trying random actions. So we're going to say here episodes equals 10, and then for episode in range 1 up until episode plus 1, episodes plus 1, like that. We're going to just get the state of the environment when it's reset. So we're going to say state equals environment reset. So everything from scratch. We're going to get the default or the initial state. We're going to say done equals false. So we're not done with the simulation yet. The score is 0, which is also just the default. And then what we do is we say while not done, we want to take an action. And the action can be, as I said, moving to the left or moving to the right to balance the stick or pole. So we're going to say action equals, and the action is encoded as 0 or 1. So 0 meaning going left and 1 going right. And from this action pool, we're going to choose a random action. We're going to say action equals random.choice 0, 1. So we pass a list with 0 and 1, and the action is going to be chosen at random. And then what we want to do is we want to call the actual step function. So we want to say environment.step, and we want to take this action. So we want to take either 0 or 1 as an action here. And this function returns now 4 values, at least in this version of OpenAI Gym. I think in more modern or more recent versions, it returns 5 values, but we only need 4. So we need the n_step, or actually we don't need all of them. I think we only need the reward and the done, but so basically we could also just leave that as an unnamed variable here, so as a placeholder. So the first parameter, or the first return value, is not important to us. The second one is the reward. This is important to us because we want to know, now my system is lagging, we want to know if this step that we took made things better or worse. And if the reward is positive, it means that the action was actually good. So it was an action that led to a better state. So each action basically changes the state, and the state that we are now after this action is either better or worse or the same. And depending on that, we're getting a reward, which can also be negative, then it would be a penalty. So we have this reward here. Then we also have done, which is, we're going to name this done because then it will also set the value of this variable here, and this basically means, okay, now the simulation is over. We lost. In the case of the cart pull environment, that means that the cart pull lost the balance, and now we lost, basically. Game over. And then we have a last parameter, info, that we're not interested in. So what we want to do here, with each iteration, we want to add to the score the reward. And remember, if it's negative, we're going to subtract it automatically because we're adding a negative reward, so we're subtracting from the score. And we want to also render the environment with each iteration. So we want to actually see what's happening. And by the way, for this, I think we need to also install an additional package. I'm not sure if that's necessary, but I think if you want to see what's happening, you need to also install, how is this pronounced? Pyglet, P-Y-G-L-E-T. This is also a package that is necessary for that, for this render step here. And with each episode, we also want to print episode number and score, whatever the score is. And when I run this now, or actually in the end, we need to also close the environment, but when I run this now, you're going to see that this is basically the simulation. You can see how the balancing is happening by going left or right. The reason why you don't see the full thing is because we end the loop when the simulation is done. If I don't do this, if I say while true instead of while not done, you're going to see the complete fail. So when I run this here now, you can see this is what happens here. Now we don't stop the simulation because it fails and we just keep going. We don't terminate after it's done. But you can see that the random actions going randomly left, randomly right does not really make much sense here. So we basically lose. Yeah. And the reason we don't see all of this when we do done is because at some point it's clear that there's no way to rebalance anything, so the simulation is over. Not while done, while not done. So this is what we get with random actions. A score of 22, 40, 23, 16, 92, 30, not very high. So most of the time below 30 or 40. Occasionally you might get to 90 as you see here. So this is what we get with random actions. Now let's train a deep neural network on this to perform better than this. For this, we're going to just import a couple of more modules here, or functions and classes. We're going to say from tensorflow.keras.models, we want to import the sequential model. Now, for some reason, my PyCharm doesn't recognize Keras. I have it installed. For some reason, it marks it as red, but it still works. So from TensorFlow Keras models, we want to import sequential. From TensorFlow Keras layers, we want to import the dense layer, so a fully connected layer and a flattened layer. From TensorFlow.keras.optimizers, we want to import the Atom Optimizer. And then we want to also, using Keras RL2, we want to import from rl.agents the DQN agent, so the deep, I think this was deep Q learning agent, which is basically Q learning is reinforcement learning, so, or one type of reinforcement learning. And from rl.policy, we want to import the Boltzmann Q policy, and from rl.memory, we want to import sequential memory. By the way, for this video today, I'm going to show you how to do all of this. If you want a video or a video series or separate videos, multiple videos on the theory behind all of this, on the theory behind neural networks, I mean, for neural networks, I have some videos, but if you want to have mathematical, theoretical explanations of what is actually happening behind the scenes, let me know in the comment section down below. If there is enough demand, I will make some videos. But for this video, we're going to focus on just the implementation, on the practical parts. So we're going to import and use. Now, after we create the environment, what we want to now have is we want to know how many states are there. So how many different states can I have? And for this, we're going to say environment.observation space.shape, and we're going to get the first dimension of this. This is the amount of states that we have here. Then we also want to have the amount of actions. We know that we only have 2 here, but we can also get this dynamically from each environment by saying environment.actionspace.n. So that is that. And what we want to do then is we want to say, or actually, maybe first of all, let's comment all of this out. Let's see how many states and actions we have. So print states, print actions. What's the problem here? Okay, so one thing that could help is going into the command line and saying pip install, and what's the package protobuf. We can set it to this version. Maybe this is also just a compatibility issue. Protobuf, and then equals 3.20. Let's see if that solves the issue. Let's run this again. And seems like it works. Deprecation warning, but there you go. Okay, now it works. So this fixed the problem. I don't know if you guys are going to encounter the same problem, but if yes, you just have to install the correct version that the error message is telling you to install. So let's get back to the code. So we have now, I didn't look at the states. I think it was 4 states and 2 actions. And what we want to do now is we want to build a neural network that is going to solve this task. So we're going to build a deep Q learning agent that is going to have a neural network model behind it. So we're going to first start by saying model equals sequential. And then we're going to say model.add. We want to add a flatten layer first with the input shape equal to 1 and states, so 1, 4 in our case. Then we want to have a dense layer, so add dense layer with 24 neurons and an activation. And of course, you can play around with these values, right? You can use 32 neurons, you can use 100 neurons. You can see what happens when you change these values, these hyperparameters. So action or activation equals ReLU, rectified linear unit. We're going to copy this. We want to have one more of those layers here. And then we want to say model.add dense layer with 2 neurons, so action space neurons. And the activation here should be linear. So this is going to be our underlying machine learning model. And then we want to take this and turn this into a deep Q learning agent by saying the following thing. Agent equals DQ agent, and the model is going to be set to model. The memory is going to be set to sequential memory. The limit will be set to 50,000. The window length will be set to 1. The policy we're going to set to Boltzmann Q policy. NB underscore actions is going to be actions. NB underscore steps for warm up, we're going to just use 10 here. And the target model update is going to be 0.01. I think that's like the learning rate or something, approximating that. So this is the agent that is using this model behind the scenes. And now what we want to do is want to say agent.compile with an Atom optimizer and a learning rate of 0.001. The metrics that we want to evaluate here is the mean, absolute error. And we want to then say agent.fit on the environment with 100,000 steps. We don't want to visualize the training process. Now you can also visualize the training process if you want to. This is also, by the way, important. We want to remove this render mode human here again so that we don't have to constantly see the training process. If you want to see it, you can do it. You can do that. But I'm just going to say false and verbose equals 1 to get some information. And then we're going to say results equals agent.test in the environment with 10 episodes. And this we're going to visualize so that we can see actually the final result. And then we want to also get numpy mean results.history. We want to get the episode reward, the mean of that. So we also need to import numpy as np. And in the end, again, we want to close the environment. So again, let's just briefly recap before we run this. We create the same environment, we get the amount of states and actions, we create a machine learning model, a neural network model, we create an agent, a deep Q learning agent with that model, with sequential memory, with the Boltzmann Q policy, with some other parameters. We compile this model using the Atom optimizer, we fit it onto the environment without visualizing the process of training, and then we evaluate this agent. We try to see how it performs on the environment, and this is something that we display, and then we also get the mean reward per episode. So let's run this and see what happens. It starts up, and then it does some training. There you go. We get a lot of deprecation warning, I think because of the versions that we're using here. But this is now training for 10,000, what is it, 10,000... steps, so training steps essentially. And I think this is only going to happen once, so we can just wait for this. We're not going to have multiple epochs. And once this is done, it's going to try the testing. It's going to start the testing, and we're going to see how it performs. And the goal is, of course, to not lose balance at all. So this is interval 2. Why is that? Where did I provide this? Oh no, I think the thing that we're doing is we're training it for 100,000 steps, so it's doing 10,000 steps 10 times. So we're going to skip that part, and I'm going to come back to you once it's done. All right, so now it's running, and you can see how it performs. It balances the poll quite well. It's still going. This is, I think, the first run, and it's not failing at all. So I think if it... There you go. We have a reward of 500, which is the best you can get. And if it now would lose balance, you would get something around 300 maybe, but you can see that it always gets 500. So it mastered the task. It doesn't fail. It basically keeps the balance, and probably you could run this for, you could probably run this for hours and it would not lose balance most of the time, I guess. So yeah, we're going to stop this here. Maybe we want to run this with one less zero, just so we can see that it's maybe not enough to just use 10,000 steps, because then it's trained, it's not random, it will perform to some degree, but it will not be the same as training it for 100,000 steps. So this was basically the perfect agent for this simple problem. I think if we train it just 10,000 times, it might end up being perfect, but most of the time it will probably not have mastered the task. It will have to be trained a little bit more to perfectly master the task. So let's just wait for this one epoch here, and then we can see what the performance looks like. There you go. So it does work to some degree, but you can see it failed here. So it gets 188, which is way better than random, but you can see it loses the balance. Yeah, this one was not good at all, 128. And occasionally it might score 500, I don't know, but it is not perfect. But the one that we trained for 100,000 steps was kind of perfect. So yeah, this is how you do deep reinforcement learning in Python. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. Also, don't forget to check out IP Royal, the sponsor of this video today. You will find them at the link in the description down below. And of course, as always, subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.